Welcome back, everyone. For this lecture, we're going to discuss the remaining rhythms that we use on a 4-lead ECG for evaluation. Rhythms that originate in the middle of the heart, the AV junction, the bottom of the heart, the ventricles, as well as discuss some of the blocked rhythms. As a reminder, let's review the conduction system for the heart. The primary foci of electrical activity for a normal conduction system in the heart is the SA node. Its intrinsic firing rate is 60 to 100 beats a minute. And as that begins to fail, the foci will move from various areas around the atria and eventually land its way into the AV junction. This is the middle backup. The AV junction has an intrinsic firing rate of 40 to 60 beats per minute, and it takes over when the atria fail. The final failsafe is the ventricles. The ventricles have an intrinsic firing rate of 20 to 40 beats per minute, and it really does serve as the last resort for electrical origin. When we talk about the electrophysiology of junctional rhythms, there are some things that produce some changes within the QRS and P wave relationship. We typically see two types of quote-unquote P waves when we look at junctional rhythms. The first is a buried P wave, and this occurs when the electrical foci is higher up in the junction. And this means that the atria and the ventricles are depolarizing at the same time, and so the P wave is present, but it's hidden within the QRS complex. Likewise, in lower junctional rhythms, the ventricles may depolarize slightly before or significantly before the atria depolarize, and this results in a P wave that would appear to be inverted and after the QRS complex. This inversion is a nature of how the ECG machine tracks electrical activity because the electrical activity is moving upwards into the atria as opposed to downward from the atria to the ventricles, thus creating the mirrored complex. As we did with all of our previous rhythms, we're going to use our same 5-step process for determining our underlying rhythm. But here's another example for you for looking at how that P wave may be hidden within the QRS complex. Okay, starting from the top of our process, we'll look at regularity. In this rhythm, the junctional rhythm, the R to R interval is completely regular. Each R to R interval is consistent across the strip. When we look at the rate, we note that the rate is less than 60. We're approximately 47 to 50 beats per minute, depending on the method that we use, clearly below the 60 intrinsic firing rate for the SA node. So we'll put a flag in that area and come back to it. Now we'll move on to the waves. Do we have P waves? Are they present and upright and rounded? In this ECG, we have no P waves at all. Likewise, we can't really distinguish the P to QRS interval or P to QRS ratio, and we cannot determine the PR interval because it's absent. One thing to note here though, even though we have absent P waves, our QRS duration is still less than 3 small boxes. It is still considered narrow. This is the hallmark of a junctional rhythm, an otherwise sinus-looking rhythm without P waves and a rate less than 40. When we have the same rhythm, but we accelerate the rate above the intrinsic firing rate, we have what's known as an accelerated junctional rhythm. This is a junctional rhythm with a rate greater than 60, but less than 100. Junctional tachycardia is the junctional rhythm, otherwise normal junctional rhythm, with a rate greater than 100. This would be junctional tachycardia. When the junction begins to fail, we move to the area of last resort, and this is the ventricles. We see significant changes in the ECG tracing when we begin to look at ventricular rhythms. These are hallmarked by slow rates. Remember that our intrinsic firing rate is 20 to 40 beats per minute, and wide QRS complexes. These are going to be QRS complexes that have a width greater than 0.12 seconds. We'll look at each of these more closely, but here are a couple of the ventricular rhythms. Notice the wide aberrant appearance of the QRS complex. These are oftentimes slow until they're very, very fast and can degrade into chaotic, irregular rhythms like you see at the bottom. The baseline rhythm for the ventricles that we'll talk about first is the idioventricular rhythm. Again, using our same 5-step process, we'll start with regularity. Is the R to R interval regular across the QRS complexes? Yes. Looking at our rate, our 6-second method gives us about 40 beats per minute. We exceed the capacity of our big box method calculation, and if we go to the small box method, we see that we're about 36 beats per minute. Moving into our waves, are there P waves? There are not. Therefore, we can't assess the P wave shape, we can't assess the P to QRS ratio, or the PR interval, so we'll put a flag in each of those three. Looking at our QRS duration, we are significantly greater than 0.12 seconds. This is the classic idioventricular rhythm, a rate between 20 and 40 with a wide QRS complex and no P waves present. Next will be the accelerated idioventricular rhythm. This is an idioventricular rhythm with a rate between 40 and 100 beats per minute. So above the intrinsic firing rate, but less than 100. Next will be ventricular tachycardia. Ventricular tachycardia is regular, has a QRS duration greater than 0.12 seconds, and a rate greater than 100. Just like the other ventricular rhythms we discussed, we cannot discern P waves, and we cannot determine the PR interval or the P to QRS ratio. These rates will often exceed 200 to 250 beats per minute and can be extremely fast. A variation of ventricular tachycardia is torsades, or twisting or turning around the point. Note the twisting structure where the QRS amplitude is large and then moves to a smaller amplitude, then a larger amplitude, almost like you've taken a long sheet of paper and twisted it around itself. This is hallmark of torsades. Again, if we look at our regularity, the R to R interval is largely regular. Our rate is significantly greater than 100. We have a wide QRS complex with no identifiable P waves. Ventricular fibrillation. This is when the heart has finally started to completely erode away and is no longer functioning to a point that it's perfusing at all. We cannot determine regularity because we do not have any QRS complex to identify an R to R interval. Our rate is immeasurable. We have a highly chaotic baseline with no real discernible wave or function, so we cannot determine P waves, QRS duration, or PR interval. This is ventricular fibrillation. In fibrillation, another way to think of the word fibrillation is quiver. And so you can just imagine that in this rhythm, the ventricles are just quivering and we're capturing that electrical chaotic nature that's occurring there. The agonal rhythm is oftentimes a random beat in an otherwise period of electrical silence. This can be a sinus beat, it can be an aberrant ventricular beat, or any other random dying impulse of electrical activity that you may see in an otherwise electrically silent ECG. And that brings us to asystole. And asystole is electrical silence overall. There's no activity in the baseline, there's no regularity, no rate, no waves, no PR interval, and no QRS duration. Okay, now let's look at some of the alternate cases. For this, we're going to look at things like premature complexes, PACs, PJCs, or PVCs, as well as pre-excitation and some of the blocks that are present. First of all, let's look at a PAC. A PAC is a premature atrial complex. This is an atrial beat that just occurs ahead of its normal appearance, and it's followed by a compensatory pause. What you see on the highlighted beat for this rhythm strip here is we've marched out the normal R to R interval and instead of that third beat occurring at its what would normal be its normal place, it is shifted closer to its preceding beat. But it's followed by a larger R to R interval to allow compensation and restoration of that normal R to R interval phase for subsequent beats. All of our premature beats are going to appear this way. They're all going to appear early and then have a period of pause afterwards. What differentiates the PAC, the atrial complex, versus the premature junctional complex or the premature ventricular complex is simply the shape of the complex that's occurring prematurely. We can see here that the premature complex has a P wave, the QRS is narrow, it meets the hallmark criteria of an atrial beat, and so we'll call it a premature atrial complex. In contrast, this complex that has occurred early in an otherwise sinus rhythm has no P wave present. By definition for junctional rhythms, because there are no P waves present in this beat, this would be a premature junctional complex, indicating that the electrical foci for the premature beat came from the junctional area of the heart. These are PVCs. These are premature ventricular complexes. Premature ventricular complexes are often signs of an irritated or slightly hypoxic heart, and the heart is firing PVCs as a compensatory tool to try and get extra blood flow either through the coronary arteries or through systemic circulation. PVCs, just like the other premature complexes, will occur early, but they're hallmarked by a wide and aberrant QRS structure. If you note in all three of the highlighted complexes here, there are wide QRS complexes. This is what notes a premature ventricular complex. These can also occur in patterns, and we name those patterns. They can occur in couplets, triplets, or salvos, which is the grouping. So they may come 2 at a time, 3 at a time, or 4 at a time or more. And they may occur in either bigeminy, trigeminy fashion, where every other beat is a PVC or every third beat is a PVC. All right, as a refresh for our normal sinus rhythm here. Our normal sinus rhythm has an intrinsic firing rate of 60 to 100, an upright P wave, a 1-to-1 P to QRS ratio, a narrow QRS complex, and overall regular. Understanding the normal sinus will help us understand some of the variants. Firstly, let's look at some changes with the PR interval itself. This is a normal sinus rhythm with a first-degree AV block. A first-degree AV block is an otherwise normal sinus rhythm with a PR interval greater than 0.20 seconds. So a normal sinus rhythm with a PR interval of greater than 0.2 is classified as a normal sinus rhythm with a first-degree AV block. Normal sinus rhythms with shortened PR intervals are considered pre-excitation syndromes. So as you can see here, we have an otherwise normal sinus rhythm, completely regular. Our QRS duration is less than 0.12. Our rate is between 60 to 100. Our P waves are upright, rounded, and present and exist in a ratio of 1-to-1 with our QRS complex, but our PR interval is shortened. This is noted as pre-excitation syndrome. There are several syndromes that have shortened PR intervals. One of the most common that we'll talk about in paramedic school is a syndrome known as Wolff-Parkinson's-White syndrome. Wolff-Parkinson's-White has the P wave that mushes itself into the QRS complex, creating a delta wave appearance to the QRS complex. The P waves are still there, but you have a merging of the QRS complex and the P wave together, which creates this delta wave, hallmarked by the orange arrows on the screen. This denotes specifically a pre-excitation syndrome of Wolff-Parkinson's-White. Let's talk about second-degree AV blocks. We have two types of second-degree AV blocks. Again, keeping in mind our normal sinus rhythm as a baseline. We'll go through our same process here, and we'll identify some characteristics that are hallmark of our AV blocks. Looking at regularity. Everything appears to be regular, with the exception of there being periods of electrical silence. This looks familiar to the sinus arrest rhythm we talked about, with one distinct difference. The period of electrical silence that exists here contains a P wave. So as we go through and we look at regularity, we're overall regular with the exception of these missing beats. Our rate is between 60 to 100 beats a minute. When we look at our P waves, we have P waves that are present and upright and rounded, but our P to QRS ratio is no longer 1:1. And this is the trick for identifying second-degree AV blocks, whether type 1 or type 2. When your P to QRS ratio, when you have more Ps than you have QRS complexes, it indicates the dropping of a QRS beat. In a second-degree AV block type 1, the PR interval increases slightly until you reach the drop beat, and then it resets. Notice our PR interval on our first complex and compare it to our second complex. Then compare that to our third. The PR interval is getting longer and longer with each complex until eventually we reach the fourth P wave, which has no QRS complex associated. Then we have the fifth P wave and the associated QR complex, and then it stretches for the next, stretches even further for the third, until it drops the fourth. This is a second-degree AV block type 1. The only difference between a second-degree AV block and sinus arrest is the presence of a P wave. That presence of a P wave differentiates it. And the only difference between a second-degree type 1 and a second-degree AV block type 2 is the PR interval. When the PR interval is constant and it results in a dropped beat, that is a second-degree AV block type 2. Now for the final blocked rhythm, the third-degree AV block. The third-degree AV block is a complete disassociation of the P and the QRS complex. Essentially, the P wave is firing at its own normal, regular rate, and the QRS complex is occurring at its own normal, regular rate, and there is no association between the two. You can march out the P waves, and there's a consistent P to P interval. You can march out the R waves, and there's a consistent R to R interval, but neither one is communicating with the other, and they're each dancing to their own dance. This is the third-degree AV block, a complete disassociation. As we finish this up, I know we've gone through a ton of information. We've got a handout tool that we'll provide you guys in class. We'll also provide links to. That is a one-page front and back handout that kind of helps break some of these components down. Remember that the key to being successful in ECG interpretation is to ensure that you practice. You have to practice this skill regularly. You're going to get it wrong. You're going to get it wrong early, and throughout your career, you're going to make mistakes. And that's okay. Just make sure that as you're practicing, you're working your way through and helping yourself develop the skills so that you can interpret this when it really matters. And practice, practice, practice. I've said it before throughout the series, and I'll say it again, that rhythm interpretation is as much of an art as it is science. These tables on the screen here will help get you the science piece that you need. But the art comes with practice.